today what we're going to talk about is the overall structure of an atom. So what you're looking at right now is periodic table of the elements. So this periodic table of the elements displays in an organized manner that we will talk about later all of the atoms of different elements that we know of. So we've got hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine. Our whole group of noble gases, including helium, neon, argon, krypton, xenon, radon, the halogens. Now, these are very, very different from each other. If your significant other was going to give you a ring or a necklace, and you had your choice of whether that was going to be made of gold or copper, what would you choose? I'm thinking you're not going to choose copper. If we've ever had any jewelry made of copper, what we figure out pretty quickly is it starts to turn bluish, greenish. Whereas the gold, well, you know, it's bling. It never loses its shine. There's absolutely nothing that's going to turn this gold any kind of different color. There's very different chemical and physical properties from copper. Oxygen and nitrogen. Our atmosphere is mostly nitrogen. Just a little bit of oxygen, and it's a good thing because we need the oxygen to facilitate one of the most important chemical reactions in our bodies and other living things. Both gases right next to each other on the periodic table, but nitrogen is not flammable and oxygen is. So very different chemical properties. Different elements, and all of them ultimately composed of atoms that have the same essential structure. So if all of these different elements are made of atoms at the fundamental level, how can they be different? What makes gold different from copper? What makes oxygen different from nitrogen? Okay, so that's what we're going to talk about today. We're going to talk about, at its most fundamental level, what makes one element, or the atom of one element, different from the atom of another element. And they're all called atoms, so how are they the same? Why do they all have the same name of atom? When, depending on the atom, it's going to impart a very different chemical and physical property to the element. Okay, so that's our focus for today. Today the title is called Atomic Fundamentals. Each element is made up of atoms with a common structure. center of an atom what's it called? The center of an atom. The nucleus. Is composed of protons and neutrons. And surrounding that nucleus are layers of orbiting electrons. This is an incredibly simplistic view. What you have to keep in mind in terms of everything that we talk about in chemistry this year is that we use our direct senses and we use instruments that extend our senses past what we have developed to deal with our macroscopic world. So we've developed these tools, this technology, so that we can see down closer and we can see out farther. And we gather all kinds of data. And from this data, we come up with hypotheses. We come up with ideas that explain the data. And of course, all of those ideas are based upon things that we know already. And so I think what's really important that we keep in mind as we talk about chemistry, and especially when we talk about the atom, and we're going to talk about the atom a whole lot more. This is just a very quick overview of the fundamental structure of an atom, is that it's our best guess from the data. It's our best explanation from the data. Does that mean that that's gonna encompass the whole reality of what an atom is? Absolutely not. Absolutely not. And as a matter of fact, they have just found data, they've just gathered data at the Large Hadron Collider to prove the existence of this theoretical subatomic particle called the Higgs boson, which is very, very sub, and it is what imparts mass to matter. And this has just happened. And so the more we know about the atom and the particles and the subatomic particles that make up the atom, the more we realize we don't know, and we can ask more questions, and we can design more technology to try to answer those questions. So the story is unfinished with the atom. So let's not think that we are complete experts about the nature of matter. We're not. But there are things that we do know, and we're very solid about, and that's what we're going to talk about today. Okay, so protons, neutrons, and electrons. So every element, gold, copper, silver, hydrogen, is made up of atoms with a common structure. So the center of that atom, center of all atoms, we refer to as the nucleus, and it's composed of protons and neutrons. And then surrounding that nucleus are layers of orbiting electrons. Okay, so protons, neutrons, and electrons are known as subatomic particles. Are known as subatomic And they themselves are made up of even smaller particles, muons, gluons. And so what they do, right, at the Large Hadron Collider is they just accelerate these atoms, well, actually particles, protons, neutrons, and electrons. I believe protons. And actually, I'm not sure. And they accelerate them to this really, really intense velocity, and then collide them. And once they collide them with this incredible amount of force, because they're traveling so fast, then they just break apart, and all those little pieces that they're made up of then can get broken apart from this massive collision, and that's how we can figure out the smaller and smaller and smaller pieces that they're made up of. But we're not talking about that. We're talking about chemistry. We're not talking about particle physics. So for us, this is really all that matters for us in chemistry, are protons, neutrons, and electrons, and we don't need to go down any further to know what these things themselves are made up of. Okay, so let's compare these three subatomic particles. We're going to make a table to do that. Okay, so we're going to put the name and the relative mass and the charge. So we have the proton, and relative mass, meaning relative to each other, it is one atomic mass unit, and its charge is +1. Positive, negative. It's just words that we are applying to this phenomenon of force, which we observe as opposite. Okay, so we say the protons have a relative mass of 1 atomic mass unit, and their charge is +1. Neutrons are also 1 atomic mass unit. Actually, a little tiny bit more, but for what we're doing, this is fine. And they don't have any charge. They're neutral. So their charge is none. And finally, we have the electron. And its mass is 1,840th atomic mass unit. Tiny in terms of mass, tiny in terms of mass. But does it have charge? Oh yes, it has charge. So even though it's got this little tiny mass compared to the proton and the neutron, its charge is equal but opposite in magnitude to a proton. So its charge is -1. Okay, so electron has a negative charge, proton has positive charge, and neutrons have no charge. All right, so there's lots of things that we can talk about here. First of all, neutrons. They are actually composed of a proton and an electron together. And the proton and electron are held together by something we call the weak nuclear force. And when neutrons spontaneously decay in radioactive decay, which we'll talk about later, they will spit an electron out of the nucleus, leaving a proton. So a neutron is actually a proton and electron connected together with the weak nuclear force. Okay, now, electrons orbit the nucleus. And so what keeps them orbiting the nucleus are these positively charged protons because we know the positives and negatives attract. Okay, now, one more thing we'll talk about very quickly is that this nucleus is composed of all of these positively charged protons and neutrons. Okay, what do positives and positives do? We know that positives and negatives attract. What do positives and positives do? Positives and positives repel. So how can it be that protons with positive charge can stay in very close proximity to each other? Well, neutrons help to stabilize a little bit. They kind of get in between the protons and keep things stabilized a little bit. But there's also something called the strong nuclear force. Okay, what's the nature of the strong nuclear force? Particle physicists could tell you a lot more about that than I can. But the strong nuclear force is actually what allows these protons to stay together in this very tiny space we call the nucleus without repelling each other and completely exploding. And then we'd have no matter whatsoever, we'd have no atoms. So the strong nuclear force keeps all these protons in this very close area within the nucleus. The weak nuclear force is what holds a proton and an electron together to form a neutron. Okay, so most of the mass of an atom is where? Most of the mass of an atom is in the nucleus, but the volume of an atom comes from the layers of orbiting electrons. Okay, and we will talk more and more about this, but I'm going to move on. Okay, so what is next? Atomic number is the number of protons in an atom of an element. And it is basically the fingerprint of an atom. It is the number of protons in an atom, its atomic number, which gives a particular element its identity. So let's go back to the periodic table and have a look at where we can find this periodic table. Okay, here we are back with the periodic table of the elements. Okay, so atomic number tells us the number of protons that are in a particular, that are in the atom of a particular element. Okay, so if we look at iron, okay, here's iron. I'm just going to zoom in on iron. Okay, how do I know it's iron? Well, I just know Fe is iron. You guys have a periodic table that lists the name of the element as well as its symbol. Okay, so I don't expect that you know what the symbols stand for at this point, but you will, because this is the periodic table you'll use for the AP chemistry exam. Don't get nervous. You'll know the names of the elements. You'll know what symbol stands for what by the time you take that exam. Okay, so here's iron, and we've got this number up here, and that is the atomic number. And if you notice, you guys, the periodic table is arranged in numerical order of the atomic number. Okay, so what this tells us then is that iron has 26 protons in its nucleus. Cobalt has 27 protons in its nucleus. Nickel has 28. Copper has 29, silver has 47, and gold has 79. Okay, and that's it. That's what makes gold different from copper. Fundamentally, it's the number of protons in the nucleus of the atom of that particular element. And so what that ought to make you think is, well, those protons, they have a lot of effect on the both chemical and physical properties of a particular element in a direct and an indirect way, which will take us months to fully understand the subtleties of that. Okay, so this is the atomic number, and it stands for the number of protons in a particular element. Protons in the atom of a particular element. If you get an atom and it has 74 protons, you know then that that atom is an atom of tungsten. Now, does that mean that all tungsten atoms have 74 neutrons and 74 electrons? Absolutely not. We cannot make that assumption at all. But if we've got an atom and it has 74 protons, we know that it's an atom of the element tungsten. What I'm going to do is I'm going to write down the rest of these notes, because then I've got to go back to having the overhead up. And I don't want to stop, keep going back and forth and back and forth. So we're going to get the rest of these notes down, and then I'm going to try to show you what the heck these things mean. Okay, so to figure out the number of neutrons in a particular atom, the number of neutrons is found by subtracting atomic number from the mass number. Atoms with there's really no way of getting around this. I'm going to have to get the periodic table back up on the screen. Okay, let's try this. So the number of neutrons in a particular atom is found by subtracting the atomic number from the mass number. So this is actually the atomic mass, not the mass number. So how do we figure out the mass number from the atomic mass? Well, it's very easy. All we do is round the number. So the mass number for carbon is 12. The mass number for boron is it 10 or is it 11? Okay, I hope that you know that it's 11, and that you know with this point H you're going to round up to the next whole. So you guys, mass number is a whole number. We take the atomic mass and we round that number, and that gives us the mass number. Okay, so let's do two easy ones that we don't have to round. We've got fluorine here, and fluorine has a mass number of 19. And it has an atomic number, which is the number of protons of 9. So we are going to subtract those two. Okay, so this is atomic number, which is equal to the number of protons. Okay, so we are going to subtract the mass number. This is for fluorine. We're going to take the mass number, subtract the atomic number, and that's going to give us 10. And that tells us then that there are 10 neutrons in most, notice most, atoms of fluorine. Not all, most. Let's look. All right. Let's go to boron. Right there. Boron has, do it here. Boron has a atomic mass of 10.811. So that means its mass number is 11. Its atomic number is 5. We're going to subtract those two. We're going to get 6 neutrons in most atoms of boron. Notice, people, I'm saying most, not all. Okay, so what's that all about? The most. Why can't we say all? All right, we cannot say all because of what we're going to look at right now. Atoms with equal numbers of protons but differing numbers of neutrons are known as isotopes. Of an element. So atoms of a particular element come in a few different varieties. For instance, carbon. There are 3 varieties of carbon atoms, 3 isotopes of carbon atoms. There is carbon 12, there is also carbon 13, and there is carbon 14. Radioactive, unstable. Okay, so what we see is they've all got this 6 down here, and you probably know what that 6 stands for. Okay, the 6 is the atomic number, or the number of protons. So we're going to write down atomic number. Okay, so they're all carbon because all of these isotopes of carbon, all of these varieties of atoms of carbon have 6 protons. So it's carbon because there's 6 protons in the nucleus of the atom. But what these 3 varieties, these 3 isotopes of carbon have different numbers of are neutrons. So this up here stands for the mass number of each of these isotopes of carbon. So we've got, we call this isotope, we call this thing carbon 12, and this is how you'll see it written, carbon 12. This is carbon 13, this is carbon 14. Okay, so this variety of carbon, this isotope of carbon, has 6 protons, and if this is its mass number, 12 minus 6 is 6. So carbon 12 has got 6 protons and 6 neutrons. Carbon 13 has got 6 protons, but how many neutrons does it have? It's got 7. And carbon 14 has got 6 protons, and how many neutrons does it have? It's got 8, right? 14 minus 6 equals 8. And this is actually what imparts its instability. It's got too many neutrons for its number of protons. Okay, so all elements come in a variety of isotopes. Okay, each isotope of a particular element, each isotope, I'll tell you in a minute.
Okay, that's fine.
Okay.
Can you use this?
Yeah, I'll take it. Okay, so each isotope of a particular element has the same number of protons, because that's what makes it carbon, but differing numbers of neutrons. Okay, one more thing and we're done for today. All right, if we look at the periodic table of the elements, what we find is that all of these elements have atomic masses that are a decimal number. Why are they decimal numbers? Why aren't they whole numbers? Well, that's because each of these elements have a variety of isotopes of its atoms, knowing that all of the isotopes have the same number of protons but differing numbers of neutrons. And so what the atomic mass represents for us is a weighted average of the different isotopes of a particular element. So, if we look at carbon, and we see the carbon has an atomic mass of 12.011, why isn't this 12 or 13 or 14? Well, because carbon comes in 3 different isotopes. And what this will also tell us, you guys, because it's a weighted average, is that by far the isotope of carbon that is most common on Earth is carbon 12, because our atomic mass is closest, is very, very close actually to just straight 12. So the majority of atoms of carbon on our Earth is of the isotope carbon 12. So that's the last thing I'm going to write on the board, that atomic mass is a weighted average of all the isotopes of a particular element. Okay, so atomic mass on the periodic table is a weighted average of the masses of all the isotopes of that element. Okay, we'll do problem set tomorrow and we'll talk about it. So don't panic if you don't understand some things.